This is Dr. Anthony Revis with SVSU, General Chemistry 111, Chapter 3, Lecture 2. That's Lecture 2 of Chapter 3. In this chapter, we will cover formula mass, molecular weight, and the mole concept. We'll also discuss determinate empirical and molecular formula. We will also take a look at combustion analysis, as well as molarity. These topics will be covered, but not necessarily in that order. Percent composition in chemistry is calculated like any percent composition in math. You take the part, divide it by the whole, times 100, and you have your solution. Mass percent composition of a compound can be calculated using molar mass. The total mass of each element is divided by the molar mass of the compound multiplied by 100. The element in question is the part. The molar mass is the whole. So therefore, you'll have mass percent composition equals the mass of each element divided by the molar mass of the compound times 100 according to the formula. It is that straightforward. For example, if we had sodium phosphate, we could calculate the mass percent of each of the elements in this chemical formula. For sodium, that would mean 3 times the molar mass of sodium divided by the molar mass of sodium phosphate times 100. For phosphorus, since we only have one phosphorus, it would be 1 times the molar mass of phosphorus divided by the molar mass of sodium phosphate, which is the exact same molar mass for any of the elements in this compound. Likewise for oxygen, in this case it would be 4 times the oxygen molar mass divided by the total mass. So again, percent composition is calculated in chemistry like you would do percent composition in anything. So let's work through a problem. If we had C2H6O, this is ethanol. What would be the percent composition of each of the elements in ethanol? So we would take the number of each of the elements, use a molar mass to acquire the elemental mass in the composition, and divide it by the total mass of the compound. In the case of carbon, this will be 2 times 12, divided by the total molar mass of ethanol, which is 46.07, and we get approximately 52%. We would do likewise for hydrogen, will be 6 times the molar mass of hydrogen, which we get from the periodic table, which is 1.008 gram per mole. But in doing these calculations, we will oftentimes simply put in grams as the unit, divided by the molar mass of ethanol for approximately 13%. And we do the same thing for oxygen, the 1 oxygen times 16 divided by the number of grams in its molar mass. And we would get approximately 34%. And we can check our calculations simply by adding them up. So again, percent compositions are straightforward percent calculations like any standard math. Let's just walk through one more example. In here, we have phosphoric acid, and we want to calculate the composition of hydrogen, phosphorus, and oxygen. We would do the same thing as we did in the previous example. We would take 3 times the number of hydrogens divided by the molar mass of the acid, 1 phosphorus at 30.97 grams divided by the molar mass, and oxygen, 4 oxygens divided times 16 divided by the molar mass gives us 65.31 in this case. So there you have it, 2 examples of percent composition based upon the formula Therefore, we use the molar mass of the elements and the molar mass of the compound. So what about percent composition by mass? Percent composition by mass will work the same way. The part divided by the total. Let's take a look at this example. A 10-gram sample of a compound is determined to have 2.5 grams of hydrogen and 7.5 grams of carbon. The 10 grams is the total mass of the compound. In the laboratory, this student has discovered that they had 2.5 grams of hydrogen in it and 7.5 grams of carbon. Therefore, the grams of carbon divided by the total grams of the compound times 100 gives 25% hydrogen. Percent carbon is 7.5 grams divided by 10 grams to give 75%. All of the calculations for percent composition can be worked by these methods. Occasionally, when we're doing chemistry problems, we have to convert percent composition to moles. This example will show you how to do that. Lecture 1 of Chapter 3 also has some examples. So let's take this example for a review. If we have 100 grams of ascorbic acid and we have 40 grams of carbon, 4.58 grams of hydrogen, approximately 54 grams of oxygen, how many moles of each of these would we have? From those moles, then, we can determine the empirical formula. And again, this is based upon understanding concepts about percent compositions. So, the first thing we do is assume 100%, which in this case, we exactly have. So that works out well. When we have 100%, or at least 100 grams, we can directly substitute in the percentages for the grams or the grams for the percents. If we calculate through here, then we take the moles of carbon, do a crossbar dimensional analysis with a conversion factor using 12.01 in the denominator. The numerator is 1 mole of carbon. To convert to the number of moles of carbons, we take the other percent of hydrogen, which we call grams in this case. We do the unit analysis, again dimensional analysis of this gives us 4.54 to be exact mole of hydrogen. And then with oxygen, we have 3.406 moles of oxygen there. We can take these now and do the ratios where the smallest value is on the bottom and the largest value on the top, and it gives us an empirical formula. So this shows you how to do empirical formulas using percentages. We've also practiced this in Lecture 1 of Chapter 3. Now, a particularly useful area where the understanding of moles, grams, molar mass, and percent composition comes in handy is in an area called combustion analysis. So what is combustion analysis? Well, combustion analysis is a process by which the elemental compositions of hydrocarbons can be determined based upon a gravimetric method. In other words, the elemental composition of organic materials, hydrocarbons, can be determined by combusting a sample and analyzing the residue. We'd like to remind you that combustion requires fuel, an oxidizer, and heat to function. That is the basics of the so-called fire, combustion, burning triangle. How does this process work in the laboratory? In the laboratory, a weighed sample of the compound is heated to a high temperature under a stream of oxygen gas. Oxygen's the oxidizer. The compound is the fuel, and the furnace is the heat source. This results in complete combustion to yield gaseous products of known identities. Complete combustion gives carbon dioxide as the carbon species. Incomplete combustion, by the way, gives carbon monoxide. This diagram shows you how the process works. You have the sample that's loaded in the furnace. The oxygen gas, the oxidizer, is passed across the fuel sample in the furnace, which is the heat source. It is burned to generate carbon dioxide and water, and it's passed through an absorber, and then the carbon dioxide is also absorbed and the oxygen comes out. So then you would take the sample from the first absorber, the water absorber, from which you could obtain a mass, and you would take the second absorber, from which you could obtain a mass of carbon dioxide. The carbon dioxide would be related to the carbon content in the sample. The water would be related to the hydrogen content in the sample. So consider this example. A combustion analysis of a 0.00126 gram sample of polyethylene, which is used for storage bags, by the way, yields 0.00394 grams of carbon dioxide and 0.0016 gram of water. What is the empirical formula of polyethylene? The reaction sequence is shown here, and the equation is unbalanced. Balancing the equation to carry out the combustion analysis in the furnace is not required. However, at the end of the analysis, you can actually go back and balance this equation as well. So, when we do the combustion analysis, the process map or the flow map for how this occurs is you would obtain the mass of CO2. Mass of CO2 gives you the moles of CO2 based on molar mass. The moles of CO2 is related to carbon based upon the stoichiometry of carbon to carbon dioxide. And then from the moles of carbon, we could convert to mass of carbon. Likewise, water mass converts to moles of water, converts to moles of hydrogen, because that's the source of the hydrogen in this experiment, and we can get the mass of hydrogen. We can take the C to H molar ratios, and we can get the empirical formula. We could also take these masses and determine the percent composition. So combustion analysis allows us to determine empirical formulas as well as percent composition. So let's take a look at the solution for this problem. To do this problem, we carry out a dimensional analysis on both of the givens, and there are two givens. And from there we'll find the moles, and we relate carbon dioxide as a source of carbon, and we relate water as a source of hydrogen. So we show you that dimensional analysis here, where the grams, the given grams of carbon dioxide, that is the given grams as in the number of grams obtained after the experiment, is that number of grams is converted to moles of carbon dioxide, which is further converted to moles of carbon. Note that there is 1 mole of carbon per 1 mole of carbon dioxide. So we use that conversion factor, and we obtain the number of moles of carbon, shown here at 8.95 times 10 to the minus 5. We carry out a similar dimensional analysis, starting with the given grams of water that was obtained from the absorber in the experiment after weighing it on an analytical balance. we obtain the 0.00161 gram of water. That is converted to moles of water by using dimensional analysis, where we crossbar grams on the bottom, and that's converted to moles on the top. And then we have moles on the bottom converted to 2 moles of hydrogen, because there are 2 moles of hydrogen per every 1 mole of water, and we obtain the given moles of hydrogen at 1.79 times 10 to the minus 4. Now that we have the moles, the empirical formula can be found as we've done in previous examples, where the molar ratio of the 2 species, carbon and hydrogen, are related to each other, with the smallest value on the bottom and the largest on the top. And when we do the simple math, we obtain a 2 mole hydrogen to 1 mole carbon ratio. Therefore, the empirical formula of polyethylene is CH2. Now, for shorter chain hydrocarbons, we could find a balanced equation for this chemical transformation, this combustion analysis. So that's how we carry out a combustion analysis. We basically take an organic sample, we burn, combust that sample, it decomposes into water and carbon dioxide if it's complete combustion, which is the goal. We then relate this carbon dioxide to carbon, the hydrogen is related to water, we obtain the mole ratios, and we get the empirical formula. One of the things that we have been talking about in this lecture without clearly stating it is a concept known as stoichiometry. What is stoichiometry? Stoichiometry is the relationship between molar quantities in reaction chemistry. So the relationship between one reactor to another, the molar quantities of those, is the stoichiometry. We can use that relationship to calculate quantities that we need to carry out chemical reactions. One of the solutions that's used in carrying out chemistry is a molar solution. A molar solution is a solution that contains a given number of moles of a solute. When we have the concentration of those moles in a liter, that's called molarity. So, the concentration of a solution is the amount of the solute present in a given quantity of solution. When that amount is measured in moles per liter, it is called molarity. So molarity is a concentration that contains a given number of moles in a liter. When we measure molarity, we always measure it against liters. So if we're given milliliters, we convert that to liters. If we're given some other quantity, we convert to liters. If we're given grams, we convert the grams to moles. Molarity is defined as moles per liter. Since it is a ratio, we can use it as a conversion factor. Keep in mind that ratios in chemistry may be used as conversion factors if we follow the dimensional analysis process with the proper math. So this slide just shows you how we prepare these solutions. You prepare them by weighing out a certain mass of material based on the number of moles you want, and you fill to a particular mark watching the meniscus line. That's usually a 1 liter volumetric flask with a given number of grams, which is equal to the number of moles, and we fill to the mark. So, let's use an example of molarity, moles per liter. A 355 ml soft drink sample contains 0.133 moles of sucrose, which is sugar. What is the molar concentration of sucrose in the beverage? As soon as you see the term molar, you think units. The units are moles per liter. So we set this up. Molarity equals moles per liter. We know that we have 0.133 moles, and we must divide that by liters. However, our given was in milliliters. We therefore perform a unit analysis in the denominator of converting 355 mils to liters by cross-hash 1,000 mils on the bottom per 1 liter. This gives us a molar concentration of 0.375 big M. The big M stands for moles per liter. And we can take the solution now and use it to carry out chemistry. Let's try another example. How many grams of potassium chromate are needed to prepare 250 mils of a 2.16 molar solution? By the way, potassium chromate is used as an oxidizing agent in many organic transformations. The first step is to determine the moles of potassium chromate in the 250 mils, or the equivalent in liters is 0.250 of this 2.16 molar solution. So we set up the equation and we start with our given of 0.250 liters of solution. We then cross-hash down using dimensional analysis the liters on the bottom, and we know that we could take liters directly to moles because moles per liter is a recognized conversion factor in chemistry, and therefore we get 0.540 moles of potassium chromate 3 sig figs. We then note that the molar mass of potassium chromate is 294.2 grams per each mole. Therefore, we take the moles and we carry through a dimensional analysis of converting moles to grams as shown, where the moles are on the bottom, grams are on the top, as a standard dimensional analysis using gram per mole as a conversion factor, and we obtain 159 grams of potassium chromate. The process works the same as processes we've used before. Dimensional analysis starting with a given times a conversion factor to the species of interest, following the units, following the standard math steps. How about another example? In this example, a chemist needed 3.81 grams of glucose for a reaction mixture. Calculate the volume in milliliters of a 2.54 molar glucose solution she would need. In this case, we're going to practice this one by using the formulas. The formula for molarity is moles over volume, the volume in liters. We can rearrange this to solve for volume, where we would have volume equals moles over molarity. Therefore, the first step is to find the number of moles. To find the number of moles, we start with the given grams, 3.81 grams of glucose. We do a dimensional analysis, cross-hash bar on the bottom with grams because our given has grams, and whatever the given has, the denominator must have in the very first conversion factor, and we convert grams to moles, and therefore we now have the moles of glucose. We would then plug this into the formula, but note that we must change the molarity concentration to milliliters. Therefore, we have the liters on the bottom, and we do a conversion times 1,000 ml solution per 1 liter of solution, and this will allow this to be converted directly to milliliters. Alternatively, you can solve this in liters and then do the conversion, whichever is easiest, okay? The math to do this, you're familiar with. As long as you follow the math rules in doing these dimensional analysis, you're okay. So you could do this by getting the answers in liters and then converting it to milliliters. Either way is perfectly acceptable, as long as it follows the standard rules of math and the process of dimensional analysis. Occasionally, after these solutions are made, you will want to dilute them. Dilution is a procedure for preparing a less concentrated solution from a more concentrated solution. This is a standard practice. Oftentimes, laboratories will prepare what they call stock solutions, and these will be highly concentrated solutions. It's a little bit like what companies do. They will ship materials to your home, cleansers, and they'll tell you to dilute it to a certain amount. So to do this, we set up a basic equality where the molarity times the volume of the first solution equals the molarity times the volume of the second solution or the final solution. The generic view of this is to call it just simply concentration. So this works for any concentration. And we point that out because this concentration could be percentages and it will work exactly the same. As long as the units are the same, the process will work out. Okay? So you can have concentration 1 times volume 1 equals concentration 2 times volume 2, or you can be very specific and use molarity. Let's work a problem. Describe how you prepare a 5.00 times 10 to the 2 mils of a 1.75 molar sulfuric acid solution, starting with a 8.6 molar stock solution of it. So we show you the two formulas here. Use either one. They're exactly the same. This could be an x1, y1 equals x2, y2 problem. If you're familiar with the math, you get it. It is that straightforward. The key here is simply check off everything that you have, and whatever you don't have in this question will be what you're looking for. So in this case, if we check through what we have in the question, in the problem, we note that the missing variable is V1. So we're simply solving for the unknown variable. We set it up in that way, we do our math, and we calculate out 102 mils. Again, this is math that we expect that students in CHEM can do, okay, on your own. All right, so practice these through, straightforward math, understand the concepts, you'll get it. Another example. In this case, we have percent solutions, but it still all works the same. A doctor orders 1,000 mils, and note this is 1,000 mils. Here has 4 sig figs because there's a decimal added, of a 35.0% dextrose solution. If you have a 50% dextrose solution, how many milliliters would you use to prepare the 1,000 mils of 35% solution? So this is again a classical C1 V1 equals C2 V2. You set up the math. The missing variable is V1. We rearrange the equation to solve for V1. We put in the mils. We put in the percentages, which are the same as concentrations. If the concentrations are the same, it will work out. The concentration can all be in some unknown unit you've never heard of, but if they're the same, they're going to cancel out. And you'll be left with the volume milliliters. And in this case, we have 3 sig figs in the percentages. Now, the percentages, again, were not standard. This was part of the experimental data or the problem-solving data. Therefore, we use these for sig figs. Another type of percent solution that we want to point out to you, and we will not be sharing any examples of it because the math is straightforward here. The percent solution here would be an example of a mass percent. In the case of a mass percent, you would take the mass of the component divided by the mass of the solution times 100. That would be mass percent. Again, any percent equals the part divided by the total. The volume percent would be the volume of the solute divided by the volume of the solution times 100. These are problems that we would expect that you can do simply by following the formula and knowing the basics of percentages. It works the way of any other percentage in math. Do your math. Mass of component divided by mass of solution times 100. Volume of solute divided by volume of solution times 100 when it's volume. And then when it's mass volume percent, There's several different units that this works out in. It just depends on the industry you're in. Doctors may use one form, they may use another form in manufacturing, whatever it is, they use different methods of doing mass volume. As long as the mass over the volume, that will be your percentage. Okay? So be aware of those, take a look at how to do those, and you'll get the idea of it. But again, it's a straightforward percent problem. Now, another important calculation that you will need to know how to do involves density. What is density? Let me explain to you what density is by telling you what it does. Density compares the mass of an object to its volume. That is what density does. It compares the mass of an object to its volume. So it has a ratio of mass per volume. So the mass per volume of an object or of a composition of matter is its density. We show you the formula for density. Density equals mass divided by volume. The most popular units for density are grams per mil, which is the same as grams per centimeter cube, which is the same as gram per cc, particularly if you're in the medical field. Density is a physical property of matter that remains the same regardless of the amount of matter. Okay? So, for example, take a look at the table on the right side of this slide. Copper has a density of 9.0 gram per mil or gram per centimeter cube. If I hold 1 pound of copper or 1 kilo of copper in my hand, the density of that copper is 9.0 gram per centimeter cube. If I load a ton or several metric tons of copper on a truck, the density of that copper is still 9.0 gram per centimeter cube. If I chop the copper into extremely small parts, it still has the same density. So, density is independent of the amount or the total pounds or grams or quantity of the material you have. One thing that you will find useful with regard to density is using it as a conversion factor. Let's take, for example, aluminum. Aluminum has a density of 2.7 gram per centimeter cube. That means that 2.7 grams of aluminum equals 1 centimeter cube, or 2.7 grams is related to 1 centimeter cube, or 1 centimeter cube is related to 2.7 gram. So you can use these then as conversion factors. So in problems where you have volume and you need to get the grams, you will often use density. In problems where you have grams and you need to get to milliliters or volume, you will use density. We show you again the table on the right side, some standard densities of many known compounds, and note they go from extremely low densities, as in gases, to very high densities, as in gold and mercury. So let's practice calculating density. Here's the problem. The mass of 50.00 milliliter sample of methanol is 39.59 grams. Determine the density of methanol. Note that the formula for density is mass over volume, mass per volume. So we have the given of 50 mils, actually 50.00 mils. We have 39.59 gram. So we simply plug these values into the formula, we run the calculations, and we report our findings to 4 sig figs. Okay? We check the units and the units work out as gram per mil following standard math practices. Therefore, we feel pretty confident about this answer. Let's practice using density as a conversion factor. Here's the problem. The density of a certain machine oil is 0.910 gram per mil. Find the volume occupied by 196 grams of that oil. We know again that density equals mass per volume. So, let's take our given. Let's also take a look at what we're after. What do we want to solve for? We want to solve for volume, and we will assume that that volume is in mils. Now, based on the formula for density, we can say that 0.910 gram equals 1 mil, or there's 1 mil related to or per 0.910 grams. Therefore, we start with our given of 196 gram. We do cross-bar conversion factor math. We run the numbers through, and we obtain 215 mils as our answer. So that's how we determine density, and that's how we use density as a conversion factor. So there you have it. That completes Lecture 2 of Chapter 3, SVSU Gen Chem 111.